shift to the next presentation. The next presentation is made by Monica Retamosa Izaguirre, and the topic is acoustic indices applied to biodiversity monitoring in a tropical rainforest of Costa Rica.
Well, good morning.
Good morning.
Good morning to all. Well, it is good morning from this part of the world at least. I'm ready to present. Well, good morning again. My name is Monica Retamosa Izaguirre, and I'm a professor at the National University from Costa Rica. Today, I will make a presentation entitled Acoustic Indices Applied to Biodiversity Monitoring in a Tropical Rainforest of Costa Rica. Tropical ecosystems undergo rapid degradation due to human activities, so there is a need of efficient and robust monitoring strategies that can um, help to adaptation, mitigation, and restoration activities. Many traditional methods are used to assess biodiversity, such as trapping, mist netting, bird counts, among others. However, alternative methods such as passive acoustic monitoring are now readily available. With passive acoustic monitoring, we can study from species that vocalize to acoustic communities to soundscapes. Advances in acoustic technologies have made possible the rapid spread of automated and remote acoustic data collection. Also, several algorithms are currently available for species discrimination and calculating acoustic indices. Indeed, much work has been done with acoustic indices to evaluate their performance as biodiversity indicators. For example, acoustic indices have been used in studies related to diversity and abundances of local species, community composition, vegetation structures, type of habitat, human activity, and ecological condition. From those studies, it has been said that passive acoustic monitoring is promising to assess biodiversity at large spatial and temporal scale. Usually, large datasets are obtained with acoustic monitoring, so there is a need to extract meaningful information from these datasets. In this sense, acoustic indices have been proposed to standardize the analysis of acoustic data, and acoustic indices have been evaluated as indicators of proxies for monitoring biodiversity. However, there is still work to be done to examine the relationship between an index and the underlying process of interest. In many studies, soundscapes have been used as indicators of change in ecological condition, with consistent and favorable results. However, the relationship of acoustic indices with traditional measures of biodiversity, for example, from bird point counts, have been promising but not totally consistent. We propose in this study to evaluate several traditional acoustic indices at two operational levels. First, at the community level, using birds as an example to assess how well acoustic indices predict bird indices. And second, at the soundscape level, using acoustic indices to classify the data according to the ecological condition of the study sites. We work at two study sites at Braulio Carrillo National Park, which is located in the central volcanic mountain range in Costa Rica. The park is crossed by the National Highway 32. This road was constructed in 1977 to connect the Central Valley with the Caribbean coast. The study was conducted at two sites between the park, each selected based on its distance from Highway 32, Quebrada, down here, um, is a ranger station dedicated mostly to public use, and it is located on Highway 32. And Seibo, up there, is a sector of the park allocated exclusively to protection and research, and it is located at about 20 kilometers away from Quebrada. The access to Seibo is by a low traffic and paved road, and there is a minimum distance of 1.5 kilometers from these roads to the sample points. Both Seibo and Quebrada sites are included in the life zone very humid tropical forest transition to pre-montane and presents an altitude between 500 and 600 meters above sea level. We use 12 sample points at each site for recordings, bird point counts, and vegetation assessment. We did this using standard vegetation plots, and we took photographs to assess vegetation complexity. We made 4 visits to each study sites from June 2017 to August 2018. 2 full days of recordings were done per visit. We did a continuous recordings from 4 to 6 a.m. and 4 to 6 p.m. and 10 minutes every hour for the rest of the day. We did not include the night. We also did 4 bird point counts per visit at peak hours of bird activities using auditory and visual detections to observe it for a period of 6 minutes and a radius of 25 meters from the observer location. With this data, we obtained 12 traditional acoustic indices, 4 bird indices, and 5 habitat variables, as you can see in detail in this slide. We would like to clarify that all acoustic indices were calculated for 1-minute fragments and then averaged by our sample point and study sites. And for analysis and to avoid biases, we use those 1-minute fragments that corresponded to the same time period as the bird point counts. For the same reason, we excluded non-vocal species to calculate bird indices using bird point count data. Finally, we like to account that bird indices do not represent actual estimated parameters at the population or community level, as we did not consider detectability. For example, richness represents observed richness number of species at each sample point, and abundance represents observed total abundance, that is the total number of individuals of all species detected at each sample point. To analyze the data, we first assess pair-based correlation of acoustic indices with bird indices using Spearman correlation. But because many authors have suggested that compound indices show superior performance over single indices to predict species richness, we used the group of acoustic indices to examine if they were good predictors of bird indices. For this, we fed a random forest regression to each bird index using the 11 acoustic indices and a 2-level factor variable for study sites as predictors. We split the data in 80% for training and 20% for testing, and we evaluated the performance of each random forest regression with 3 metrics: the normalized mean absolute error, normalized root mean square error, and coefficient of determination. Additionally, to assess if acoustic indices were good predictors for site classification according to ecological condition, we used a random forest classifier. 2 sites with different levels of anthropogenic perturbations were considered: the sites with higher level of anthropogenic perturbations, such as Quebrada, and the site with lower level of anthropogenic perturbations, such as Seibo. We used repeat cross-validation of 10 faults, which were repeated 5 times to evaluate the performance of the models, and the variable important assessments for the random forest classifier was done by permutation. All analyses were conducted using R language. Well, pair-based correlation of acoustic indices show a positive correlations of abundance, richness, and diversity of birds with acoustic complexity index and acoustic evenness index. On the other hand, We found a negative correlation of abundance width, abundance, richness, and diversity of birds with acoustic diversity index. On the other hand, the random forest regression for bird indices presented a low performance with low values of coefficient of determination R-squares and high error values when considered the normalized root mean square errors, contrary to what we expected. Furthermore, the importance assessment analysis of variables showed that the set of acoustic indices used was not a good predictor of bird indices, although diversity and entropy indices shows a better performance related to bird abundance and richness. However, the acoustic indices classify the sites with high accuracy, mean accuracy of 0.93 with a standard deviation of 0.08. The variable importance assessments for the random forest classifier indicated that the acoustic diversity index was the most important predictor. As a discussion, although we did find correlation between some acoustic indices and bird indices individually, the overall performance of the random forest regressions, when considered all indices together, wasn't good enough to conclude that acoustic indices were accurate predictors of bird diversity measures in this study, in contrast to our expectations. This is inconsistent to other studies that use the same statistical approach, possibly due to that they detected animal sounds orally from the recordings used to calculate acoustic indices instead of doing a separate bird point counts at the same time, or they considered biological sounds from different sources, including birds, mammals, and insects. However, we use an independent data set for birds using bird point counts, and we reason in some way that some circularity might occur by using the same data to compare approaches. Using an independent bird datasets might be a more rigorous approach. However, we caution that data analyzed corresponds to short timeframes where both sample methods were applied alongside and will need to be validated for extended periods of time. And also, our bird measures represent the observed assemblage of bird species during the bird counting points, but not actual bird parameters estimated for the site, as I said before. The acoustic complexity performed well to reflect bird activity in study cells, however. Acoustic diversity and even indices, although they show better performance to predict bird indices, reflected a counterintuitive relationship with bird indices. This is considering the assumption that acoustic energy distributes to a broader range of frequencies with increasing numbers of species in an acoustic communities. However, and according to some authors, this assumption is only true for the range of frequencies mostly used by birds, around 2 to 8 kilohertz. And if the energy of the biophony sounds are evenly distributed across all frequency bands analyzed. We think that given the complexity of tropical forests, diverse groups of animals make up the soundscape, so the indices seems to be reflecting characteristics of the soundscape by itself, rather than of a particular group of animals. We argue that tropical ecosystems, tropical soundscape are highly complex and portray comprehensive ecological patterns and processes that cannot be simply attributed to one or few of their biodiversity components. However, we found very promising results relating ecological conditions to soundscape characteristics in a tropical rainforest. This is a key finding for monitoring purposes of important tropical ecosystems in the face of land use or climate change, and to readily and robust inform conservation and management actions. We conclude that acoustic technologies have the potential to provide a cost-effective surrogate for for monitoring ecological conditions in tropical forests and efficiently complement other traditional sources of field information. And thanks for your attention.
Thank you very much for your perfect timing and for your very clear presentation. So I think there are many questions for you. Almo, please talk.
Yes, thank you for your kind presentation. just a comment. Working in a tropical area or in temperate area or in boreal area, the diversity, the acoustic diversity is different, because in tropical area probably there are more partitioning of frequencies, and in temperate area there are some species, especially birds, some birds that are singing across all the frequencies. So it's extremely difficult to not to compare, but to fit the diversity that the indexes are finding and the real diversity. Song thrush, Urdu surf, Philomelos, or Nightingale, the Shinya megarincos, for instance, have a very broad spectrum of frequencies and repertoire. So this is a big problem that we have, and not easy to be solved. I stress more about the utility of the indexes, every type of indices, more for investigating the quality of the environment and the condition of health of the environment. And this is much better than to concentrate or focuses on individual species and simply on biodiversity, because believe me, it's not so easy to pair biodiversity and acoustic indices. In some cases, is real problematic. It's a comment and not a question, but your opinion.
I agree.
Your opinion.
I agree with you. That's true.
Okay, another question from Klaus Riede.
Yes, hello. Okay, here I am. I like your concept of underlying processes of interest, and as an entomologist interested in insects, I have a suggestion which is somehow based on anecdotal observations. I understood that you have this counterintuitive result with the bird index contra overall index. So that means that if there is a great diversity of birds, then you don't have a big acoustic index. And I would suggest, I wonder if this is due to the lack of insects due to predators. So birds are heavy predators of insects. So with a great bird diversity, you would have less insect abundance. That would be an easy hypothesis you could test, and less insect abundance index.
I apologize. I didn't listen to the last thing you said because something is failing on my on this part. But I didn't say that we excluded, for example, we didn't exclude all the other sounds from the analysis, but when we have heavy rain, for example, or cicadas, explosion of cicadas that will dominate the acoustic space, we did exclude those 1 minute fragments for analysis. So we don't have that type of influence in the analysis.
This is a very important point. In many cases, we need to select which days or which hours to use for our analysis, and this might have an impact. So it is important to find, to define common protocols for selecting or excluding sound recordings for the analysis, or even to put all together and try to discriminate automatically all different types of sound events and sound shearings. And this could be another approach where powerful statistics can help in clustering the measured features into groups to be separated with objective criteria. But I think we have a lot to discuss about all these points. So, but we need to go on with the next presentation.